In this exercise, we'll create a decision tree from a data that we have. This data have been simulated from this decision tree, very much like what we did in the introduction notebook. This decision tree decides whether to play tennis or not, depending on three variables: outlook, humidity, and wind. Let's first import the needed packages, pandas. From scikit-learn, we're going to import tree, and then we're going to import the function export text from scikit-learn tree export. Next, let's read the data from the file dataplaytennis.csv. As you can see here, this data describes different outcomes of playing tennis, yes or no, depending on the values of these different variables or features. Before creating a decision tree based on this data, we need to map all of these categorical variables to numbers. And that's the case for many machine learning algorithms. They all require a matrix of numerical matrix of the features and a numerical vector of the outcome variable. So we need to convert these features to numbers. This conversion is straightforward in this example. I'm going to simply map no to 0, yes to 1. And for the other variables, I'm going to do the same. I'm going to map sunny to 0 or 1, overcast to 2, and rain to 3. So what I'm going to do for each one of them, I'm going to create a dictionary that maps each value, for instance, no, to the number. And I'm going to use this dictionary to convert this column to a numerical column. So I can do play tennis, apply, and then I can take my dictionary and write a function that takes each value and look up the value in the dictionary. That will basically convert the no's to 0 and the yeses to 1. Once I do this, I no longer need the original column. If I wish, I can keep it and create another column. We can call it play tennis 2. For the sake of this example, I'm just going to override the column here. I'm going to do the same for the other variables. So for outlook, I'm going to have a dictionary that maps sunny to 1, overcast to 2, and rain to 3. The next step is to apply to convert the column itself, very similar to what we have done here. Instead of converting play tennis, I'm going to convert outlook by applying the dictionary outlook. I'm going to do the same for temperature, humidity, and wind. So for temperature, I'm going to map hot to 1, mild to 2, cool to 3. For humidity, I'm going to map high to 1 and normal to 2. And for wind, I'm going to map strong to 1 and weak to 2. Once I'm done all of this conversion transformations, I have a data. My data in the data frame is all numerical. The next step is to take out the feature matrix from the data frame as well as the target vector. The feature matrix is basically the subset of the data that contains the input variables, which are outlook, temperature, humidity, and wind. So what I'm going to do here, I'm going to pull this data from my data frame. I'm going to pull outlook, temperature, humidity, and wind. And I'm going to call this one X. My Y is the outcome vector, which is play tennis in this case. Now the next step is to create a tree model. So I'm going to use the function decision tree classifier from the module tree. So tree, and I'm going to create a decision tree classifier since the outcomes are categories. Next, I'm going to use the model to fit my data, and I need to provide the X and the Y. So as you can see here, we created a decision tree classifier, and here is some information about the default parameters that scikit-learn used to fit the model to the data. We will learn more about fine-tuning these parameters. In this example, I'm going just to call this one decision tree because its function fit doesn't change the initial decision tree. It just gives you back a new decision tree that I'm going to need anyhow. The last step in this example is to basically print the tree. We're going to use the function export text to print the tree. There are many ways to print the tree, and it's also possible to render the tree. For this example, we're just going to export text the decision tree. This one shows as one string, and we want to print the string because we want to show the tree on multiple lines. And you can see here that we have multiple line feeds. In this printout, prints the features using a sequence from feature 0 to feature 2. That's not very helpful because we want to map the feature to the column names. So I'm going to supply the optional parameter called feature names. And the feature name will basically be the columns of my X. I just need to convert this to a list rather from being an index object. Okay, so this is the decision tree we have. It's basically first looking at humidity and then looking at outlook. Let's try to compare this decision tree with what we have above. I'm going to copy the text so we can have it side to side, or at least very close to the original decision tree. Now, first it's going to take a look at the humidity. So if humidity is less than 1.5, which means it's 1. So again, we coded the humidity to be high for 1 for high and 2 for normal. So if humidity high and the outlook is less than 1.5, it means the outlook is 1 in this case. The class is 0. So outlook less 1.5, it means it's sunny. So that basically corresponds to this branch. Outlook is sunny, humidity is high, do not play. However, if the outlook is greater than 1.5 but less than 2.5, which means the outlook is overcast, the class is 1, which is basically this branch in the tree. If the outlook is more than 2.5, now it's going to look at the wind. If the wind is strong, less than 1.5, it's going not to play. Otherwise, it's going to play. Class is 1, right? Otherwise, it's going to look at humidity again. We're back here. If humidity is normal and outlook is less than 2.5, it's going not to play. That particular one we don't have in the data. However, if humidity is high, it's going to play. So you can see that this decision tree mapped to the data, except that it introduced a branch that we have in the decision tree. And that's something we will have in general. In real-life applications, we don't have access to that model here. So the data itself is simulated from the model, and there are some inaccuracies here. In particular, this model overfitted the data, so we had something that did not exist in the original model. Once again, many of them we don't have access to the real model of the data, otherwise we don't need machine learning or the data generation process in this example. However, there are some mitigation we can do in order to make sure that our model stays as close as possible to the real underlying data generation model or process. This is something we will talk about in more details in the next lectures.